The following data were obtained from a skater. Now, the very first step whenever we're given a bunch of data, particularly time and position data, is to graph it. Now, to save us some time, I already graphed that for problem A, which is to plot a position versus time graph for the skater. I ended up numbering the time axis in 2-second time intervals from 0 to 20 seconds. And then for my position, y-axis, it went from 0 to 10 meters. Now, I chose this for this 10 by 10 grid because our maximum time was 16. And then I'm okay with a little bit of blank space, just to make sure that my increments were nice and evenly spaced. And then same with the positions. I'm okay with those 2 rows of blank data on the top, just so that way our data was plotted a little bit easier. Now that we have this, we can see that from 0 to 4 seconds, the position of the skater is increasing. It increases from 0 meters up to 4 meters, and that occurs over a time of 4 seconds. From 4 to 6 seconds, the position remains constant at 4 meters. From 6 to 10 seconds, the position decreases down to 2 meters. From 10 to 12 seconds, the position remains constant at 2 meters. And then from 12 to 16 seconds, the position goes from 2 to 8 meters. So, for part B, what do you think is happening during the time interval t equals 4 seconds to t equals 6 seconds? Now, realistically, we can just go with the kind of straightforward routes. The skater stops moving, because that is indeed what happens. What we can say in this region is our change in position is 0 meters. Now, the way that we can end up calculating that change in position is going to be our final position minus our initial position. Our final position, or the position at a time of 6 seconds, is 4 meters. And the position initial in this region is the position at 4 seconds, which is also 4 meters. That's how we can definitively state that the change in position is 0 meters, which supports our statement. The skater stops moving. So for part C, what do you think is happening from the time interval t equals 6 seconds to t equals 10 seconds? So 6 to 10 seconds. Well, the skater is going back towards its starting position, or the skater is traveling in what we can define as the negative direction. Now, the way that we can mathematically prove that for how do you know is, once again, just using that calculation of displacement, which is going to be our final position minus our initial. Now, it's our position at 10 seconds minus our position at 6 seconds. At 10 seconds, the position is 2 meters. At 6 seconds, the position is 4 meters. That means that in this time interval, the position decreases by 2 meters. So, when we're calculating the average velocity from 0 to 16 seconds for part D, we do not care about the individual velocities, which the instantaneous velocity, the actual velocity of an object, is the slope of a position time graph. However, we see a slope here, which is not the same slope here, 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 or here. We have 1, 2, 3, 4, 5 distinct regions of this graph. So we have 5 distinct slopes on this graph, 5 distinct velocities for this skater. But this problem is asking us to calculate the average. Now, while we could take the average by adding up all of the individual velocities, making sure that they're scaled appropriately based on how long that velocity was, and then trying to divide by that time interval, that's a lot of work. An easier way to do this is by figuring out the overall change in position, displacement, and divide it by the overall change in time. Because we're looking at the region from 0 to 16 seconds, the final position in this region is the position at 16 seconds. And the starting position here is the position at 0 seconds. Final minus initial. And we'll do the exact same thing with those times. So the final position is 8 meters. The starting position is 0 meters. The final time is 16 seconds. The starting time is 0 seconds. The position increases by 8 meters, and that occurs over 16 seconds of time. So the velocity, on average, increases by positive 0.5 meters every 1 second. While we have regions where the velocity is greater than that, This is the average velocity. Same thing with part E for the speed. Our speed is just going to be the absolute value of the instantaneous velocity. However, our average speed, we cannot calculate that as the absolute value of the average velocity. Instead, when we calculate this, we need to calculate it as the total distance traveled, or the path length, and divide it by the amount of time that has passed. So the way that I'm going to do this is to look at those regions of the graph to see how much position has changed. So from 0 to 4 seconds, the distance traveled in this first region of the graph is 4 meters. In the second region of the graph, 0 meters of travel. In the third region of the graph, while the position does indeed decrease by 2 meters, the skater still travels 2 meters. In this fourth region, they don't move, so that's 0 meters of distance traveled. And then in this final fifth region, they go from a position of 2 meters up to a position of 8 meters. So overall, they travel 6 more meters. Our path length is going to be the sum of all of the distances traveled in that amount of time. So in this case, we can go with the 4 meters plus the 0 meters plus the 2 meters plus the 0 plus the 6 meters. And all of that occurs over 16 seconds of time. So this is going to be 12 meters in 16 seconds, which means that on average our speed is 0.75 meters every 1 second.